Okay, so here's where we left off as I recall. We had a definition of Laplace transform. Our definition was the Laplace transform of some function f of t was, anybody remember?
Big F of S.
Big F of S, that's correct.
Equals the integral from 0 to infinity. E negative S T.
It was the integral from 0 to infinity of e to the negative st times f of t dt, as long as that integral converges. When you're going from 0 to infinity, sometimes integrals converge, sometimes they don't. And then I think we started to make a list. For example, we discovered the Laplace transform of 1 was 1 over s. And we discovered that the Laplace transform of t was 1 over s squared. The Laplace transform of t squared, 2 over s cubed. The Laplace transform of t cubed, 6 over s to the fourth. And in general, the Laplace transform of t to the n was n factorial over s to the n plus 1. And that works as long as n is a positive integer, like 1, 2, 3, 4, 5. All right, so we're going to continue this list today. So we're going to add some new functions.
We're going to do like the Laplace, like a log or sine or cosine or something.
Well, we're going to do e first. Laplace transform of e to the t, e to the at. Oops. K times t, those are k's. Hyperbolic cosine of kt, hyperbolic sine of kt, cosine of kt, and sine of kt. We'll find the Laplace transform for all those functions. And then we'll add one more.
So what about tan h? Would that just be the Laplace transform of cosine h over the Laplace transform of sine?
Unfortunately, it doesn't work that way because Laplace transforms are determined in terms of integrals. And if you divide sine over cosine, you don't just get to divide one integral divided by the other integral, unfortunately. So we'll talk about Laplace transform of tangent here in a few minutes also. And then the other one we're going to have is t to the x in general, where x doesn't necessarily have to be an integer. X could be like 1/2 or something. All right, well, let's do e to the at first. The Laplace transform of e to the at would be the integral from 0 to infinity of e to the negative st times e to the at dt. How do you integrate that? Absolutely, you can add the powers. You're multiplying, so you add the powers. That's the integral from 0 to infinity of e to the minus st plus at dt. Absolutely, you add those powers. Then what? How about if I write this as the integral from 0 to infinity of e to the minus s plus a all times t dt. What did I do? Factored out a t. So now this is e to some number, s and a are numbers here, e to some number times t. How do you integrate e to some number times t? 1 over the some number e to the some number t. That's exactly right. So this becomes 1 over negative s plus a e to the negative s plus a t, and we have to evaluate from 0 to infinity. And again, I'm going to use lazy notation here. I'm not going to write down the limit as b goes to infinity of all that stuff. It just, you may, since you are no longer in Calc 2, you may use lazy notation on your test. If you were in Calc 2, I would take points off for lazy notation, but you're not in Calc 2. If I do it, you're allowed to do it. I guess that's the general rule.
You're allowed to see the answer sheet.
No, you're not allowed to see the answer sheet. That's a whole other class. All right. So now, what happens when t gets really, really big? What happens when t goes to infinity? It depends on the values. What we really need is negative s plus a to be a negative number. If negative s plus a is a negative number, then I end up with e to the negative times a really, really large number that's getting close to e to the negative infinity, and that would be 0. Minus. What happens when you plug in 0?
It's 1 over negative s.
1 over negative s plus a. And that's assuming that negative s plus a is a negative number. What happens if negative s plus a is a positive number? You get e to the infinity, and then that integral would it would be infinity. It would diverge. So this is typically written as 1 over s minus a.
How do we find s and a?
Well, so the problems are going to look like this.
Oh wait.
The problem would say, find the Laplace transform of e to the 4t.
Oh, I see now.
And so a is the number 4, and when you get done, you go from a function of t to a function of s. So the Laplace transform of e to the 4t would be 1 over s minus 4.
So we'll have no way of saying that s minus 4 is a negative number?
So in this case,
Obviously,
s would have to be bigger than 4.
we just leave
Correct.
us to usually like that.
You would just leave it like that, and it's assumed that we all understand that s would have to be bigger than 4.
Okay. Yeah, good.
Otherwise, the Laplace transform wouldn't converge. Okay? All right, so we can add that one to our list. 1 over s minus a. All right, now, how are we going to find the Laplace transform of hyperbolic cosine? Do what?
Gonna integrate it, right?
So instead of putting this e to the at here, you want me to put hyperbolic cosine of kt? And then I'd have to integrate that. How would I integrate that? That would be an integration by parts problem. And it would be one that cycles around on itself. Those were a big pain in the neck. I have a better idea. There is a table somewhere, but I think what I'm going to do is I'm going to remember that the hyperbolic cosine of kt is defined as e to the kt plus e to the negative kt over 2.
Yeah.
Definitely? That was our definition of hyperbolic cosine? How does that help? Over a year ago, that's true. How does that help? Well, we talked about this the other day. If I want to do the Laplace transform of e to the kt plus e to the negative kt over 2, I can take the 1/2 out, and then I can split into 2 Laplace transforms. This was the fact that we talked about the other day, that because Laplace transforms are defined in terms of integrals, these are properties of integrals, that you can take a number out to the front. If you're integrating two things and adding them, you can integrate them separately and add them later. And so this becomes a pretty easy problem. This is now 1/2 times. What's the Laplace transform of e to the kt? We just did it. It's 1 over s minus k. A is the letter k this time. Plus 1 over s plus k, because it would be s minus negative k, s plus k. I'm going to go ahead and get myself a common denominator and add those up. That's 1/2 times, let's see, my common denominator is going to be s squared minus k squared. So this one I'm going to have to multiply by s plus k. This one I'm going to have to multiply by s minus k. I'm going to be left with s over s squared minus k squared.
So on like tests and stuff, like do we need to go through like this whole like process with the? Like, can we just like use our ones that we found and just say?
Well, you have two choices when it comes to taking a test. Choice number 1 is derive the formulas as I did. Choice number 2,
No card.
put it on your note card. Which one do I recommend?
No card.
Put it on your note card. Yes, absolutely.
There's still 1/2 in front of that, right?
No, because s plus s is 2s, and then the 2 reduces with the 1/2. All right. So there's the Laplace transform of hyperbolic cosine. We ended up with s over s squared minus k squared. Not a 1/2, because notice right here I have s plus s, which is 2s, so that 2 reduces with that 1/2. You can go through exactly the same process with hyperbolic sine, write it in terms of e's, use a linearity, and you will discover that the Laplace transform of hyperbolic sine is k over s squared minus k squared. Questions on those? Go ahead.
What's the application? What can we do with this?
What can we do with this? Right now we can do absolutely nothing with this. Why are we doing this?
So we can solve higher order differential equations.
Eventually we will learn how to use Laplace transforms to solve differential equations. Later this week we will learn how to use Laplace transforms to solve differential equations. Okay? So we're getting there. That's what they're for.
I'll let you just click, because I can get lost.
That's the big picture. The big picture is this: we will develop a technique to use Laplace transform to solve differential equations. All right. So how about the Laplace transform of regular old cosine of kt? How would you find the Laplace transform of regular old cosine of kt?
Well,
You have two choices. Choice number 1 is to write it out. E to the minus st cosine of kt dt. That would be choice number 1. And unfortunately, this is once again an integration by parts problem, which once again is one of those that loops around on itself. And those are kind of a real big pain in the neck, as I recall from my days in Calc 2. Any other choices? Trust that I have the answer. I don't have the answer. Somebody smarter than me had the answer.
Were you ever taught how to actually find these out by hand?
No.
Is there a class?
Well, I know how to do it. I can do the integration by parts. I can do it and make it work. Pain in the neck, but I can do it.
To write it in terms of
You go talk to Leonard Euler. Remember that formula we had where we took e to a complex number? You can take cosine and write it in terms of e's to complex numbers. Cosine kt is e to the I kt plus e to the negative I kt all over 2.
I don't understand the I part, the I K T and the I negative I K T. And where the I's coming from?
Remember we did this before? We took e to the ix and we plugged it into the series expansion for e to the x, and we saw that this became cosine x plus I sine x when we plugged into the series expansion for e to the ix. This was Leonard Euler's technique, maybe. Anyway, the moral of the story is, you don't have to believe me or you don't have to remember why. The moral of the story is cosine can be written in terms of e. And why do I want cosine written in terms of e? Because then I can do the exact same trick that I did for hyperbolic cosine. What you're going to have to know in the end is what we get for an answer. You're going to need this on your answer sheet. So you go ahead and you do the same thing that we did. You're going to find that the Laplace transform of cosine kt turns out to be s over s squared plus k squared. And how is that similar to the function, to the answer we got for hyperbolic cosine?
minus.
Hyperbolic cosine had a minus in the middle, but otherwise it's the exact same formula. So, the Laplace transform of hyperbolic cosine turns out to be s divided by s squared plus k squared. And in a very similar manner, the Laplace transform of hyperbolic sine turns out to be k over s squared plus k squared.
You're saying hyperbolic, but
I'm sorry, regular old cosine and regular old sine. No hyperbolics for those last two. Sorry, I was saying hyperbolics, you're right. Questions on that? All right, so the last Laplace transform we're going to talk about today is the Laplace transform of t to a power in general. The Laplace transform of a power function is usually expressed in terms of this new function called the gamma function. And the gamma function is defined as the integral from 0 to infinity of e to the minus t, t to the x minus 1 dt.
So is that like inverted L, that's gamma?
That's capital gamma, that's correct. It's capital Greek letter gamma. All right, so here's what you need to know about gamma. The important things to know about gamma. Gamma of 1 happens to be the number 1. That one's easy to prove. Just take 1 and plug it in right there. You get t to the 0. So you just integrate e to the negative t. You get 1. Easy to check. Not so easy to check, and I'm not going to verify this for you. You can take my word for it. Gamma of 1/2 turns out to be the number square root of pi. That's interesting. Obviously, right, of course. And then gamma has a recursion in it. Gamma of x plus 1 happens to be x times gamma of x. And then here's the answer. The Laplace transform of t to a power is gamma of a plus 1 divided by s to the a plus 1. So if I have a number like 1/3 here, it's going to be, if a is a third, then it's going to be gamma of 4/3, which turns out to be a factorial if a is a positive integer. But if a is not a positive integer, then it's gamma of 1/3. You'd have to plug 1/3, 4/3 into there, integrate, and see what you get. All right, so there's our last.
Wait, can I ask a question now?
You may.
So, the Laplace transform of T to the A. So, do you even need to know gamma? Can't you just look at the factorial part of it? Not worry about gamma?
Well, let me ask you a question. That works wonderfully as long as you pick numbers that are integers.
Oh, sure. We just talked about that. Never mind.
What if I want to know the Laplace transform of t to the 1/2?
Yeah.
Well, according to what we just said, this is going to be gamma of 1/2 plus 1 over s to the 1/2 plus 1, which is 3/2. So that's gamma of 3/2 divided by s to the 3/2.
That's it?
How much is gamma of 3/2? Something with a pi in it, that's correct.
Oh,
So now we have to use this little rule here that says gamma of x plus 1 is x gamma of x. So in this case, x plus 1, x is 1/2. So this is 1/2 gamma of 1/2 over s to the 3/2.
Pi over 2.
1/2
Square root of pi.
square root of pi, which you could write as square root of pi over 2, s to the 3/2. So there would be the Laplace transform of t to the 1/2. Not so bad. It gets worse? Okay. What about the Laplace transform of t to the 1/3? Well, that would be gamma of 1/3 plus 1 divided by s to the 4/3.
Does that become 1/3 cube root of pi over s?
That becomes 1/3 gamma of 1/3 over s to the 4/3. Unfortunately, I don't know what gamma of 1/3 is. I only know, the only two I know gamma of 1 and I know gamma of 1/2. How much is gamma of 1/3?
Is that third?
I don't know.
I don't know either. What you would have to do is take this integration formula, plug in 1/3, and then attempt to integrate this thing. The good news is, you don't do that. There's your answer. You leave it just like that.
Oh, thank God.
Okay. I'm sure somewhere there is a table of values for the gamma function. I don't know them. The moral of the story is when it comes to doing problems out of your book, you're always going to have a 2 on bottom. It's going to be 1/2 or 3/2 or 5/2 so that you can eventually reduce it to get this square root of pi in there.
So say it was 5/2, it's gamma of 5/2. It would just be what, 5 times the root pi? Or?
So gamma of 5/2 would be gamma of 3/2 plus 1.
Oh.
So that would be 3/2 gamma of 3/2. And then you would write that as 3/2 gamma of 1/2 plus 1.
Wait, I'm kind of confused. Like,
Before when we had a half, we just added 1 to it. And now we're splitting 5 over a half into 3.
I'm still kind of confused with that. Like, 3/2 gamma 3/2 thing. Like, how is it going from gamma 3/2 plus 1 to 3/2?
That's one of the properties of the gamma function.
Oh, I-
Gamma of 3/2 plus 1 is 3/2 gamma of 3/2.
Okay.
Okay, so what you would have to do if it was a 5/2 is you'd have to use that property once, right? 5/2 is 3/2 plus 1, which allows you to pull a 3/2 out and make that down to a 3/2. And then you do it again, you write 3/2 is 1/2 plus 1. So then you would have 3/2, you'd pull the 1/2 out, then you'd have the gamma of 1/2. And now you have something you know, gamma of 1/2 is square root of pi. So the final answer would be 3/4 square root of pi. Okay? All right, the rest of the stuff we have in this section. Bunch of theorems. This one we talked about last time. The fact that the Laplace transforms are linear. And we used this a couple times today. We used this to find the Laplace transform of our hyperbolic cosine. We used it to find the Laplace transform of hyperbolic sine, regular cosine, and regular sine. All right, the next thing we have, a new definition. A function is piecewise continuous on the interval a to b, provided a to b can be divided into finitely many abutting subintervals, such that f of t is continuous on the interior of each subinterval, and f of t has finite limits as t approaches each endpoint. The heck does that mean?
This is rough for a Monday, George.
This is rough for a Monday? All right, so what this means is you have some interval from a to b. Basically, you're going to split a to b up into a bunch of different regions. And you're going to have a function that's going to be continuous on each subinterval. So your function might look like this. There's a continuous function. There's a continuous function, and then like so. So that would be a piecewise continuous function. Each piece is continuous. And notice that when I approach an endpoint, any of the endpoints from either side, I'm not blowing up to infinity or blowing down to negative infinity. They don't have to be going to the same thing. The limits just have to be finite.
So it just means if you put all pieces together, it would be continuous.
Yeah, basically what it means is you have a series of jump discontinuities. So if I could move this one up here and connect it, and then move that one and connect it, and have one continuous function, it would be continuous. Basically it means you have a bunch of continuous little pieces, but you don't have any vertical asymptotes, because these limits all have to be finite. Once I have a vertical asymptote, I'm no longer piecewise continuous. Next definition. F of t is said to be of exponential order as t approaches infinity if there exists m, c, and t such that f of t is less than or equal to m e to the ct whenever t is greater than or equal to t. Once again, convert that to English. Basically what this is saying is f of t is of exponential order if it's eventually smaller than some exponential function. So I guess the question is, can you give me an example of a function which is not of exponential order? Cosine is of exponential order.
Oh, you're right.
Because cosine, f of t equals cosine t, looks like this. Is it eventually smaller than an exponential function? Well, exponential functions look like this. So is the cosine function smaller? Yeah, almost always. Cosine is definitely of exponential order. Well, can you give me a function that's not of exponential order?
Zero.
Which one?
Zero.
0 is of exponential order, because 0 would look like this. In fact, 0 is smaller than every exponential function.
Wait, what's the question again?
Can you give me a function which is not of exponential order?
What is the definition of exponential order?
It's right up there.
Oh.
X squared is of exponential order. Because x squared is eventually smaller than e to the x, or let's make it even easier, x squared is eventually smaller than 2 to the x. For example, if you pick x to be 4, 4 squared is 2 to the 4th, those are equal. For any number bigger than 4, this function is now bigger.
Hyperbolic.
Hyperbolic cosine is of exponential order because hyperbolic cosine is just two exponential functions added together and then divided by 2, so it's even smaller.
Tangent.
Yeah.
Natural log is of exponential order. Tangent, there's one, I finally heard one. Tangent, I do not believe, is of exponential order because tangent has asymptotes which are bounded in between. If I draw an exponential function, exponential functions are eventually going to cross that asymptote, aren't they? So eventually the tangent will be bigger than the exponential function for any exponential function. So tangent is a function that is not of exponential order. So somebody was asking, what about the Laplace transform of tangent? Well, here's the answer. If f of t is piecewise continuous and f of t is of exponential order, then it has a Laplace transform. And we just said that tangent was not of exponential order.
Or it does not exist.
Therefore, it is not guaranteed to have a Laplace transform. And as far as I know, it does not have one. Maybe it does. I'm just not aware of it. Okay?
So, like for a problem, we probably just beat F to prove that something is guaranteed.
Yes.
Which is like something that's
Yes. All right, the last thing we have in this section, once we have Laplace transforms, we of course have inverse Laplace transforms. So, for example, just a minute ago, well, more than a minute ago, we said the Laplace transform of t was what again?
1 over s.
1 over
S squared.
s squared. So the inverse Laplace transform of 1 over s squared would therefore be t.
Oh. Let's see.
So it's like squaring and square rooting, right? You go forward, you go backward. It's like integrals and derivatives.
Oh, and here it comes. Yeah.
Yep.
No, not yet. Not today. But we will need inverse Laplace transforms in order to solve our differential equation. So we're getting closer. So what's the inverse Laplace transform of 1 over s cubed? It's not t squared.
Oh, wait, no.
Because, remember, the Laplace transform of t squared was what? 2 over s cubed.
1/2 t squared.
Yeah, it's kind of like doing u substitution. I really need a 2 there, so I sneak a 2 in there like I need it. It looks like a 21 now, but it's really just a 2. But since I'm going to multiply by 2, I've got to divide by 2. So this would be 1/2 t squared. What's the inverse Laplace transform of 1 over s minus 5?
It's getting at everybody close.
It's got to have an e in it. E to the 5t. Because you might remember our rule for Laplace transform of e to the kt, or e to the st we use, but same thing, 1 over s minus k.
So what if it was just the Laplace transform of s minus 5?
What if it was the Laplace transform of s minus 5?
Or the inverse maybe.
Well, first off, it would not be the Laplace transform of s minus 5. It would be the inverse Laplace transform of s minus 5. What's the inverse Laplace transform of s? We don't know. That's the correct answer, because I would be asking you the Laplace transform of what gives you s, and we don't have a rule for that. So the answer is, at this point, we can't answer that question. I don't know that it doesn't exist, but I do know that I can't answer that question at this point. What about the inverse Laplace transform of s plus 2 over s squared plus 9?
Would be 1/2 hyperbolic sine of 3 or something.
Nope. We're going to be dancing around.
Oh, it would be straight sine. Be 1/2 cosine. 3.
All right, well, I'm going to split my fraction on my numerator. I'm going to write it as inverse Laplace transform of s over s squared plus 9 plus the inverse Laplace transform of 2 over s squared plus 9. And then I go look on my chart. Do I have an s over s squared plus 9 on my chart? Yes, that's a cosine 3t. S over s squared plus k squared. That's cosine 3t. Plus, how about this one?
Yeah. Kind of.
Kind of. What do you mean kind of?
You gotta multiply the top k.
Right. The one we want to use is this one. The inverse Laplace transform of k over s squared plus k squared is sine kt. The problem is I got a 3 squared down here and I got a 2 there. I need a 3. So how do I turn a 2 into a 3? I multiply by 3 halves, which means I need to balance that by multiplying by a 2/3. So you're going to end up there with 2/3 sine 3t.